People do trip.
The irony is there's so many found on the south rim, they're not worth a lot. Yeah, I mean, they're just worth about $1 a gram. See, 100 gram iron ain't $100 rock. The type and the rarity, yes. You got a calcite, you got a Martian or a lunar, and you hit the jackpot. And there has never been a lunar found in the West Coast. Yeah, the most
I wish you good luck.
Thank you. Appreciate you.
I'll be watching it.
Stephen Smith. Stephen Smith, what's up? So if you got lots of salt, you can't cover it in. How would that be different?
According to your feet. Well, the batteries they told me to hold off because that's number two, where technology
Okay, that's the book. Okay, yeah, you see this here? Mesquite, Vanderbilt. You basically start out here. Logan, yeah. Okay, so you go here to this here, you go down there, and about here, this is the work, and about here is Clyde Bundy's Ranch. Okay, so you start out taking going from Clyde Bundy's Ranch. Yeah, you start here and you go south for about 57 miles. This is the Arizona border, this is Nevada. And you go south all the way down to about here, and then you got to head down to the bottom of the canyons, the Tri Canyons, and then you got to head back up. And I'm actually on a rim over here near and I'm going to do Jungle Peak. Yeah, I'm actually south of Jungle Peak. I'm about here on the rim. Literally on the rim. So here, probably right here. Probably right there. And that's the rim right there.
first of all, I'm in Phoenix, so I had to fill up the tank a few times. And I spent about 10 days out there. Several trips.
I'll tell you what, man, I love shooting.
It's really pretty.
And they got music now. Saw that? I'm gonna put some on.
Here's pretty milk bad.
This one called Space.
Cell phone about 47 miles away. Across Grand Canyon in Meadville, Arizona. You know, up there. So I forget on the other side of the canyon. Climbing mountain one night to get up and climb the mountain. So not very good. That's where I was at. It was pretty cool out there. Kay's gonna need one of the meter only ever people out there. Very good. Those are the most dedicated people in
Australia. Watch it. Australia.
They're more dedicated than I am. And they do better than I do. I don't find them. They fight. Anyway, it's interesting. Yeah, it's straight south to Kingman.
Still driving. Still driving.
And they didn't have great
drive.
Yeah. Probably about 3 miles.
I make that not being able to hear, but I also not being able to understand people's sign language.
Maybe on the downside of the other see. It's got a small property. So that actually is pretty accurate. For that low. Anyway, it is pretty accurate.
Welcome, everybody. Welcome to our first general. Oh, sorry.
It's not good for me.
All right. Can you hear me all right? Welcome to our first general meeting of the Texas Star Party for 2022. We have a number of announcements today. I've learned one part of this job is that people throw announcements at you, so we've incorporated them all, and we're going to gallop right through them because we know everyone's eager to hear our featured speaker tonight. So just to review the basic rules of the road, 9 p.m. remains dark out, 7 p.m. remains gate closing, and 5 miles per hour remains the speed limit on the road. If you bought prepaid t-shirts, you still have quite a stack of those which have left unplayed. So please go up to the registration, to the sales information desk and get your t-shirts. Tomorrow we're going to have the presentation of the Omega Centauri, Lone Stargazer, and John Wagner's Astronomer's Award. So that's something to look forward to tomorrow night. I'm going to ask our chair to come forward and talk about the special program. Chair of the board, George Ellis.
Thank you, Scott. Just a couple of quick announcements. First of all, a safety announcement. How many people think they can walk around in the dark on a ranch with their eyes closed? You've been here so many years, right? The reality of this is that you can't do it no matter how much you think you can. We want to encourage everybody to remember to please carry a red flashlight with you, not a white one, but a red one. Everywhere you go on the ranch, watch your step, and if something should happen, and trip or fall or anything, please make sure either you or a bystander, someone close by, lets the staff member know so we can take appropriate steps to see your safety. And that's all I'll say on that side. The other thing is, you may have seen some posters around the ranch about the John Wagner Student Astronomy Award. We lost John Wagner this past December, and John, as many of you know, has been a staple at the Texas Star Party for decades through his work with managing the observing programs. And because of that, we realized that we wanted to do something special to remember him. And since he was such a devoted teacher, and he believed very much in familiarizing youth with amateur astronomy and the universe, we decided to set up a youth award. And that's going to be announced and presented tomorrow night. And to help us fund that and other youth initiatives, we set up a raffle, which some of you may or may not know about. That raffle tickets are for sale in the back while the sales desk is open. And we want to encourage you to buy a raffle ticket. We've got a couple of good prizes here. One is for $570 at Walker Star Convention 12 miles. The other is for pre-registration camping at next year's TSP. So raffle tickets are $20, and all money goes to furthering the youth outreach initiatives at the Texas Star Party.
Thank you, George. Now I'd like to recognize the president of the organization, Carol Walls, which has announcements from the individuals to all of us.
Hello and welcome to TSP 2022. I'd like to sort of deviate this a little bit from my script. I would like to recognize the real heroes of TSP 2022, but all the volunteers who have helped prepare during the weekend, the weeks, months prior to even getting here, those who assigned to housing, and those who are running the event currently. Would you all please stand up and give each of you a round of applause? Thank you for all your hard work, your dedication, and commitment. Without you, TSP would not be the premier event that it is. The Star Party that everybody wants to come to. And thank all of you for coming under such awkward times as we are experiencing these days. Let's hope that 2023 doesn't have us in the same set of circumstances, and we can go back to some of our less rule-based ways. A couple of things to talk about real quickly. Don't forget, if you were on the dark-out team, you have to be here Sunday to remove the paper from the windows and to change up the light bulbs. If you were on the power grid deployment team, you likewise need to be here on Sunday in order to take up the power cables, twirl them together into the trailer. So important dates. If you got a pen and paper, if you want to put this into your cell phone. And remember, this is conditional based on our pending contract. But the dates for TSP 2023 are March 14th through the 20th. I'm sorry, May. I misread May and 14th. I'm going to blame it on Tired Eyes. And on 2024, it will be May 5th to the 11th. Okay? Now, the most important announcement I have to make is for Saturday. As a thank you to all of you, Texas Star Party is going to treat you to an ice cream social in the dining hall, catered by 8 Bears for Boost Ice Cream. They will also be on the site tomorrow in the pavilion. That's on your day. Saturday night is on ours. So please make sure you stay, come over into the dining hall and enjoy the ice cream on us. Okay? That will start at 7 o'clock and end at 8. So basically right after dinner. And as you finish your ice cream cups, please put them in the trash can. You can bring your own things to drink, your own snack, but again, let's clean up behind ourselves. And we'll make the same announcement tomorrow. Any questions? I have one. I see one in the back. Yes, May 14th to the 20th, 2023. May 5th to the 11th, 2024. We do 2-year contracts in Ranch, that's why we have 2 days for 2023 and 2024.
As a help to the dark out team, if you don't want to be awakened to retrieve the red lights early Saturday morning, please pull out the red lights, set it on the front porch, pull the paper down, set it on the front porch. We won't disturb you.
Exactly.
Carl, repeat that, he says.
What was it? If you do not want to be awakened at an early hour on Sunday, replace the light, a red light bulb with a light, and put the red one on the porch. Take your blackout material, roll it up into a ball, put it on the porch, and you won't have somebody knocking on your door. Like one of the 3 bears coming back for breakfast. Any other questions? I have one. Are y'all having fun?
Yeah.
Isn't it great to be back at Texas Star Party? Thank you very much for coming. I having y'all enjoy working with y'all and being of service to you. Thank you.
We just recognize the volunteers right now. If you would like to volunteer for future TSPs, sometimes we have to wait till we ask. So we're asking. In the back table, we have a box with some yellow index cards, with a sign that says volunteer for future TSPs. So feel free to write your name, your contact information, and then if you particular, if you could help that. Your help would be much appreciated. It's that volunteer spirit which keeps this organization working. I'd like to recognize on the Senate note, the mellow music provided by FM TSP Radio, 90.1 on your station dial. So if you haven't listened to our TSP music channel, feel free. It'll put you in the mood. I'd like to recognize 2 special friends of the Texas Star Party. The first is a lawyer. His name is Ted Saker. Is Ted here tonight? Ted?
That's fine.
Okay, well, Ted contributed a great deal to our effort.
There he is.
Take it out, Ted. Ted provided enormous help in drawing up our COVID protocols, helping with the bylaws, doing the things which are just too expensive for full-time lawyers to handle. So he did it out of a sense of help to us. So really appreciate that.
I'm responsible for this day.
I also want to recognize Ken Francis, who year after year has done all the certificate awards that we have. We give out a lot of certificates. We are apparently a very self-congratulatory group. And Ken, thank you very much for your help on that. And I guess that concludes the official announcements. So I'll turn it over for our speaker, and to introduce would be Robert Reeves.
They all probably respond to this. Previous certificates. The Spacecraft 2019 had a result. I was producing the studio there. I can put in my presentation like Dan Durda about time during the past. Of course, they'll know you as the moon man, so that was a fascinating talk for me. And I thought so much of that talk that he got me to close his mouth, and I was already poaching for the Texas Star Party. So, gets our party canceled, gets our party canceled. So 3 times we tried to get in here and it worked. He's here tonight. Dan Durda is a planetary scientist with the Southwest Research Boulder operation. His life goes on forever. So in order not to have one of the classic 1980s dating meeting time introductions where the introduction was longer than the presentation, I won't go through all of that except to say he's extremely accomplished in his field. But personal level, he's a private pilot. He's a diver, scuba diver. He's also a cave diver, which in the hierarchy of diving is pretty high up there. Other interesting things that he does, he's the coach for the zero-G researchers who fly on the zero-G paraglider to study microgravity experiments. And he's also involved with the Orion folks over at Van Horn, getting ready to fly microgravity experiments on the Blue Origin flights. And then, in fact, already booked on one of the other Branson's, whatever the thing is, I think about so sooner or later, he's going to go on carbon line, and he will be technically an astronaut as well. So without wasting much more of his time, I'll turn it over to Dan Durda.
Thank you, Robert. I'm going to do a couple of contexts here. Is that going to be too loud, too quiet? How you guys hear me in the back of the room? All good? Am I blowing you up on over here up front? All right. Okay, cool. Well, I guess we'll start there. Thank you, Robert, for the invite here to Texas Star Party. It's my first time here. I can't believe I've missed it all these years. I'm really happy to be here, and it's really nice to see a couple of familiar faces out there from Spacecraft. So a little bit of overlap between our communities, so to speak. Oh, hey, look at that! It suddenly magically appears in the world. Well, that's nice. Sorry, I'm talking to myself as I'm looking through the thing here. Okay, great. The laser pointer I want to use. I started in this field. What got me involved in this field in astronomy as a 10th grader back when Carl Sagan's Cosmos came out in 1980 was, Carl's fascination with extraterrestrial life and exoplanets and all that kind of fun stuff wore off on me. That's what really got me interested in the field. But by the time I arrived at grad school at the University of Florida, my advisor, who actually worked with Carl at Cornell, was more interested in things having to do with asteroids and dust in the solar system and where that dust came from. And he very quickly put me onto a project to look at the collisional evolution of asteroids. And ever since then, my whole career has been focused on these little rocky worlds, and as I like to tell people, basically making molehills on the mountains, because it's ultimately grinding the big ones into small ones as it goes. So my whole career has been focused on impacts and disruptive stuff. So the talk I had given Space Fest those 2 years ago that Robert saw was focused on this kind of research, and it's still near and dear to my heart, and let's go and explore some of that. We live in this amazing, amidst this amazing collection of little tiny rocky worlds, the asteroids, that literally are fossils of formation. They are, in a sense, the fossil building blocks of the planets, especially the inner planets, and our own little rocky world included. They literally are those remnants. They are the main asteroid. Well, first of all, start with the UR here, so that Texas Star Party located right there. Third drop from the sun. The orbits of the terrestrial planets here in blue-green sort of color. The main asteroid belt out there, are primarily between Mars and Jupiter. Is this entire huge collection of leftover remnants, leftover planet dust. When the first asteroid was discovered in Ceres, it at the time fit this idea that there ought to be some sort of another planet out there in that region. That was rapidly followed by the discovery of a few more, and then many more, and then an embarrassing, rich collection of too many rocky worlds out there. Very quickly, the idea became that maybe these are the remnants of a planet that used to be there that broke out. And we now know very well today that that's not the case. It's the remnants of a world that never came together. And it's really the remnants of worlds that never came together, because the main belt as we see it today, much of the material originated in that zone of the solar system. Some of the material out there in the outer main belt was implanted there from further out in the solar system, beyond the orbit of Jupiter, out around the gas giant planets. During the celestial billiards period of the formation of the planets 4.5 billion years ago, a lot of material was being moved all through the solar system, some of which ended up in the main asteroid belt from way far around. But that's a little peripheral to the story today. The main belt, these green objects out here, occasionally those objects are perturbed by the gravity from the giant planets, primarily. Perturbed a little bit from the actual sunlight. We'll talk about that in a little bit more detail later on. Some of those main belt worlds will find themselves on orbits that cross into the inner solar system. Eventually, some of them evolving into orbits that remain in the inner solar system. All these little red objects here represent the near-Earth asteroids, many of which we're exploring today. So, just to give you a little bit of context that way. This is a fun little picture. I just want to give you some context for the size, the scope of the world that we're exploring here. These are not planetary objects large enough to have been rounded by their own self-gravity. Many of them are fragments from collisions between larger objects in the past. Some of them are reaccumulated remnants of objects that have been broken up. We'll talk about that concept a little bit, but I just want to talk about the sizes here. Eros is one of the very largest near-Earth asteroids. Small in comparison to some of the larger main belt asteroids, but amongst the near-Earth asteroids, one of the very, very largest. This is an asteroid that we've actually orbited around, and in fact, kind of inadvertently touched down on. It wasn't a planned landing by the Mir spacecraft, but we actually had physically the first landing of an asteroid from the Mir Shoemaker mission. Other objects are smaller, various sizes. I'll point to this one in particular, not because it's a particularly well-known one or remarkable in any other sense, other than its size. That's getting close to the scale of the asteroid object that impacted the Earth 65, 66 million years ago, that wiped out dinosaurs and 2/3 and 3/4 of all the other organisms on the planet at the time. So imagine Mount Everest booming up the sky and landing in the Yucatan Peninsula 65 million years ago. That is formed by an object that would have been very, very close to scale-wise, something like this guy. Now I'm going over here to another object that we've actually encountered and had mission to Iokawa. And again, in particular, I want you to kind of focus on the size here in comparison to this guy. And on the next slide, we're going to zoom in and see Iokawa to scale again, but with some other familiar objects next to it. Here is the International Space Station and the Orion spacecraft, two of them docked together. The International Space Station, in context, next to one of the actually still kind of a large near-Earth asteroid. From the perspective of things that impact our planet routinely, this is considered a large object. Okay? And you can see that compared to the space station and compared to worlds like the moon and the Earth, it's actually a pretty tiny world. Now, when it comes to the context of future missions to near-Earth asteroids, where astronauts will go someday to kind of lay the groundwork for longer duration extended missions to Mars and beyond, most likely we will be traveling to objects that are the easiest to get to and those that encounter the Earth most frequently. And a couple slides coming up now, you'll see what I'm referring to, the very, very smallest objects. By definition, some of those objects we're going to go to first are going to be the smallest ones because there are more of them. They offer more opportunities to get to. And typically, that's going to be an object more or less something like the size of one of these blocks. These little guys floating around out there in space, orbiting the sun and the Earth environment on their own, are still considered near-Earth asteroids. In fact, some of the smallest near-Earth asteroids that places like the Canada Sky Survey or Linear and so on, have observed passing between the Earth and the Moon on a monthly time scale. Some of those very smallest objects we've seen independently out there in space as their own objects are objects about this sort of scope and scale. The size of these little tiniest boulders on the sides here, on the side of the tower, are the sizes of some of the smallest near-Earth asteroids we've actually observed out there in space. And it's objects like this that are going to be our first targets for human exploration. So, how do we know about asteroids? How do we learn about them? The name itself kind of tells us that the original, the most frequent way of understanding these objects in the past is that they appear star-like in a telescope. And it is optical telescopes primarily that gave us, first of all, our first discovery of asteroids, and later on our first scientific study of them as objects out there in space, looking at their reflecting spectra, say. The sunlight bouncing off the surfaces, penetrating a few wavelengths of light deep into the mineral crystals on the surface, being reflected back to the Earth. Some of those mineral grains in there, the atoms and molecules in those minerals, picking up the vibrations of the near-infrared light, re-emitting in different wavelengths. Absorbing certain wavelengths from the sun allows us to determine what minerals are there on the surface of these objects. Looking at the change in the brightness of the objects as they rotate out there in space and present their larger sides to us, their smaller side to us, their larger side to us, creates a light curve, and we get to understand the rotation periods that way. We can understand the sizes of asteroids for occultations of distant stars. So all of those techniques with optical telescopes are ways to get information on these things. There are other types of telescopes, though. Radio telescopes and radar allow us to really kind of get human scale sort of context for the surfaces of these objects. Some of the radar observations from a sad face for Arecibo and Goldstone allow us to see boulders on the surfaces of these objects. We get near spacecraft quality observations of some of the closest near-Earth asteroids from radar telescopes. And it really highlights the tragedy and the loss of Arecibo for many other reasons, but especially from the perspective of the exploration of near-Earth asteroids and the understanding and ability for us to learn what we need to learn from the perspective of mitigating the danger of impacting asteroids. The loss of Arecibo was a severe, severe blow. It's really a big loss. Fortunately, we actually have pieces of asteroids that land on the Earth practically every day. The tiny ones, every now and then, a bigger one. The meteorites. Meteorites are fragments of asteroids that have made it through the atmosphere down to the surface of the Earth. They are direct samples of the asteroids. Most of the time, we don't know which ones. We know what kinds, but not necessarily which specific asteroids. It's a little like going on a walk at the base of the foothills of the mountains over here through a pebbly stream, and you walk down to the stream, and you can pick up the fragments of the rocks that originated up there in the cliff face, and you can kind of get some idea of what that cliff is made out of by picking up the pebbles that are down here at your feet. And that's what the meteorites allow us to do for the asteroids out there that they make down. And of course, now more recently, the very best means we have for learning about these things are the spacecraft that we send out to the asteroids. We have encountered asteroids out in the main belt as we've flown our spacecraft out to other destinations like Jupiter or New Horizons or other places. There are missions that have been dedicated to go specifically to particular asteroids, like Eros, the near mission, and more recently, a whole series of sample return missions that we'll talk about in a little bit. Really neat missions like OSIRIS-REx and Hayabusa and so on. Here's a little bit of the very first time I ever made that slide, many years ago, I included 2 missions on it because that was the only 2 missions we had. And now you can see we've got this entire smorgasbord of missions that have visited asteroids out there with the images from those missions of the actual asteroids that have been imaged. So again, dedicated missions to orbit around the largest asteroids in the Alpha Planet. There were flyby asteroids. When I started my career doing the asteroid studies, it was as a associate member of the Galileo imaging team, and I just missed the asteroid encounter, but when I arrived at the University of Arizona, we were just going through the IF encounter, and only the second asteroid ever to be visited by a spacecraft had a moon, which was an amazing discovery, because if only the second asteroid that you randomly picked to fly by has a moon, that means there's moons all over out there, which we now know to be the case. There's probably on the order of 15 or 17% of asteroids have satellites. And those are formed by a variety of means. Different causes for making those, different methods of making those moons, depending on whether you're in the near Earth population or out there in the main belt. But moons are very common. So that was a lot of fun, starting a career off looking at collisional evolution of asteroids and finding out the very second one you went to had a moon probably made by some sort of a collision. That was kind of cool. So we've seen quite a few asteroids up close. We're really good to know. Now, collisions between asteroids is how I started out my career. It's a good way to go because it's pretty much the dominant geologic process that affects most asteroids. The asteroid belt is a very crowded place out there, as we know from the Empire Strikes Back. You can barely fly through without catching your typewriter. It's actually not that bad. In fact, the reality is the asteroid, for all the millions that are out there, there are about 1 million asteroids larger than a kilometer across in the main belt. There are about 1,000 asteroids larger than a kilometer across in the Earth population. But for all of the millions of asteroids out there, when we want to fly a spacecraft like to Jupiter or Saturn or Pluto, and if we want to get a little extra oomph on our mission and take advantage of the fact that we're passing through this interesting region, let's pick an asteroid to go fly by and learn about. It's actually very hard to get the celestial mechanics to work out, to get close enough to an asteroid as you're going to your more important target to actually make those observations. So your odds of accidentally running into an asteroid as you traverse are pretty low. But the asteroids out there wandering around on their independent orbits, which aren't all perfectly circular and which do cross each other, over time, they do accidentally run into each other, where they're in the same place in their different orbits, the same place in the solar system at the same time. Just like cars changing lanes up the highway, you will get an impact. The typical crossing speed, the Earth is orbiting the sun at about 29.5 kilometers per second around the sun. As you go away from the sun, it gets a little slower and slower. But the crossing speeds, as you average them out there in the main asteroid belt, typically about 5 kilometers a second or so. That's not the orbital speed, the crossing speed, the speed at which they impact each other. About 12 or 13,000 miles per hour. That's typically the impact speed for asteroids out there. When asteroids run into each other at those speeds, I will tell you right now, it is not like the way it is sometimes, unfortunately, too often portrayed in the very science documentaries that I'm often in. You'll sometimes see in the older animations these little asteroids floating around out there, and they go they bump into each other, and then they bounce off each other. That never happens. Okay? I wouldn't say it can't happen. But the statistical chance that two asteroids on the crossing orbits are going to encounter each other so slowly is down in the 10 to minus some big number percent chance of that happening. Okay? When they run into each other, it's at thousands and thousands and thousands of miles per hour. The speed of sound in rock is only about 1 or 2 kilometers per second, especially fluffy stuff that these asteroids are made out of. And so most of these impacts are happening at faster than the speed of sound in the rock, okay? Which means that the shock wave propagated through that target is propagating faster than the speed of sound in that target. It's kind of like having a sonic boom in the rock that is being impacted, right? These things obliterate each other when they impact. They don't bounce off each other. And when they obliterate each other, nature likes to make what we call power law distribution of fragments, an exponential number, an exponentially more smaller objects than larger objects. Okay, this is, in fact, the fragment. I got bored one day at meetings to talk about in a little while, waiting for them then to set up the next run. And I took the fragments that I collected out of the chamber from one of our experiments and just started kind of arranging them on the paper. You know, bigger ones, small ones, and then got a little bit kind of really crazy with it and started lining them all up really more carefully. And ended up making a rather interesting diagram here that very visually shows you what these power law distributions look like. And the neat thing about this is it's fractal, meaning that independent of size scale. So if you break up something this big by one of these impacts, you make a distribution that looks like that. If you break up something the size of this room, or the size of, you know, the mountain that McDonald Observatory is on, you still end up making an exponential distribution, just that the bigger fragments are a bigger size. Okay, so this picture replaced this not with the fragments from my lab experiment, but scaled up to be the distribution of the sizes of asteroids in the near Earth population. So this would be like arrows, right? And then down here would be like Itokawa. And then down here are all the other little things, the size of the things that are the size of the boulders on Itokawa, the things that are as big as this room that we're in right now, which is like the size of one of the things on the side of Itokawa that you saw in that picture, right? So that's what the Earth asteroid population looks like. Imagine that. That's what's hitting us all the time. And that's what's doing stuff like this, wiping out the dinosaurs, okay, making really neat vacation destinations, breaking windows in Russia, making holes in the Chilean desert, and turning jumper cars into instant money makers for young women. This is the Peekskill meteorite, which fell during the Friday night during football season. So back in the days when the movie cameras were just coming, video cameras were starting to be popular. And so Friday night, everybody's out there videoing their kids and this bright light crossing the sky. So with multiple football games going on all across northern New York, with multiple views of this fireball coming down, we can backtrack the trajectory and verify that that fireball is the rock that fell from her garage that made that hole in the car, and we knew where it came in from in the main asteroid belt. But the really cool thing was that POS car in her garage that she was trying to sell was not moving at all. Nobody wanted to buy it because it wasn't a very good car. The next morning, after the hole in the trunk appeared, it was a few tens of thousands of dollars she was able to sell that car for, because obviously the meteorite collectors and all that kind of stuff. So it made a good story, and she was very happy about the meteorite discovery. So the collision physics that really interests me, or that got me into this part of the field, is really, for me, a lot of fun, and a lot of the science of understanding collision physics originated in the years after World War II for a couple of different reasons. Excuse me, two major themes in the post-war era of looking at craters and explosions and things like that were going on. One, we were really interested in understanding the craters and the blast effects from nuclear weapons. And then there was another group of people who were very interested in understanding the impact effects of high-speed metal projectiles hitting other metal targets. You can kind of imagine where that originates from. So it's hard to get at a lot of the physics. If you're a civilian science researcher trying to get to some of the data that was generated back in those days and looked at, it's a little difficult sometimes because it's kind of, well, we're going to fuzz out that part of the paper, we're going to black out this part, because a lot of these things are classified. So the experiments were done and the physics research was done, but for us as civilian researchers, we have to rediscover all this, as it turns out. There's another major theme, though, that was going on back in those days, around that same time, and that was the growing interest in impact craters, because we were getting ready to go to a highly impacted world. This is the run-up to Apollo, landing on the moon, and early started to understand how these circular depressions of the moon were formed. They weren't volcanoes, in fact. Like Gene Shoemaker pioneering the understanding of the impact origin of these worlds. was leading us to a lot of, Gene kind of bridged the gap between those worlds. The explosion physics world, he would go out there and study the nuclear blast craters at the Nevada test site. And then we go out to places like Meteor Crater and the volcanic craters in Mexico and so on, and compare and contrast and understand. It wasn't that we didn't know that Meteor Crater was an impact crater before Gene started working there, but Gene was the first one to really do a good job of showing why. Okay, here's this overturned flap of ejecta that preserved. Meteor Crater's in a great place because you've got this layer cake of sedimentary rock that really beautifully illustrates the overturning nature of the impact ejecta. You can document it very well, as Gene went and did the field work to document that and so on. So that's a very important basis of the work that leads to the modern understanding of these things. For me, it was an early, very important part of my career. Right when I was in grad school, 1991, making my first trip out west to a asteroids, comets, and meteors meeting in Flagstaff. Well, let me back up just a second. Back in my high school era, watching things like National Geographic and some of these other science documentaries, you see people doing some of these impact experiments or being out there at Meteor Crater, or seeing this one very famous guy taking his rifle and shooting it into sand and making impacts, and being out there at Meteor Crater. Turns out it's this guy, Gene Shoemaker, who I had been seeing all these years on TV and kind of, drumming up my interest in this sort of thing. And you sort of develop as a kid this kind of fantasy that someday I'm going to go to Meteor Crater with Gene Shoemaker, and walk around there with him, like that's ever going to actually happen, which then happened in 1991. So it's really fun to go through that process as a young scientist. They say never meet your heroes, but I can tell you, go ahead and meet them, it's okay, because they're awesome. And Gene was the best. He was just amazing that you could not help but get enthused in anything that Gene was talking about. He just oozed enthusiasm and love for what he was doing. And so, it led me down this path of wanting to get a little more hands-on experience with this process and learning how this stuff works. And the way I go about it is a little bit of computer work, a little bit of numerical simulations, which I'll show you. But I really prefer really truly hands-on stuff, which is getting out to the lab and shooting big guns at a rock and playing with explosives and making craters. And that's what this is all about. Some of the numerical work, I was doing some National Science Foundation funded research around in the aftermath of the discovery of Ida. Ida's new dactyl, that little potato-shaped world on the main belt, the second asteroid that we found that had moved around it. How that new form. I started looking at the literature. People were suggesting maybe sometimes the fragments of a big collision on the asteroid may end up in orbit around it, and trying to understand that process. So some of the work I was doing involved doing these numerical models using what are called smooth particle hydrodynamics models. They're basically it's pulling all the equations that describe the heating and the compression and the fragmentation of rock as you're going through these high-speed impacts. It's the same numerical codes that they began to be using to replace the crash tests that the auto industry would do when they want to improve the safety of the vehicle, the crushability of the front end of the car, and you understand how all those things work, where they actually bash the cars together in the lab with the crash dummies inside, right? That's expensive to do. And as time goes on and computer capabilities got a lot more up there, you're able to do those crash tests in the computer. But to do that, you've got to be able to tell the computer how metal bends and how plastic fragments and so on. While the same physics codes could be used with rock, and the same physics codes were being used by the nuclear community to understand the blast physics of nuclear weapons and so on. We could apply that to asteroids and the rock that makes them up. And so I can show you what one of these little impact movies tests look like. There we go. This is a simulation of a 100-kilometer diameter rocky asteroid being struck by a 20-kilometer diameter rocky asteroid. So the projectile in red, the target in blue, and you see at those scales, it turns out that it's not just that the rocks hit each other and crack, they hit each other, and again, because the shock wave that's propagating through that rock is faster than the speed of sound, the rock doesn't even know to be able to fragment again, in a sense. It's being heated, it's being compressed, it's actually flowing more like a liquid, like a fluid, than our rock that's fragmented. Yes, it's fragmenting as it goes, but it's flowing at the same time, and that's why that impact was more like a splash than like hitting a hammer with a brick or just cracks. And that's not just some artifact of a numerical, visualization. That's a real effect. And of course, there's explosion craters. Sadly, they won't let me play with nuclear weapons, so I can't get out there and do the really large ones like Sedan, which is 104 kilotons, made a crater 90 meters across. But I have not done that test site. Walk around down into some of these same craters that Gene explored way back in the 50s and 60s. They don't let you do it for long. I got limited. The one day with 3 craters. By the time you're dressed as a bunny suit, you've got the Geiger counter with you, and you're looking at all the melted glass on the rocks, and the Geiger counter thing next to you, the needle is just pegged high. It's not even going click, 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 click. The needle is just pegged high, going, and you're walking around doing your thing. And by the time you're done with your 3rd crater of the day, and you're poking around with your geologic, hammer and stuff, and you're making your notes. The people who are there from the test site and I'm watching after you, making sure you're staying safe. By the end of the day, they're kind of like, you're done. Well, I think that, but I'd like to, you've gotten your dose of the year. So you're kind of limited, but it's a neat place to go. So I'm limited to playing with things like ammonium. Well, I guess I won't say too much about what I'm using there, but it's the fuel oil and fertilizer mix that has produced some other bad effects in other places. But this is a crater that I was working on in the Energetic Materials Testing Center associated with New Mexico Tech. It's Socorro, New Mexico. That is a really great place where you can go if you're interested in the blast effects on concrete walls or other structures and so on. You go out there to do your testing. And so for me, it was dig a hole in the desert for tobacco. And when I say me, I'm not the one digging the hole. I'm just saying, can you dig the hole for me? But can you dig the hole for me? It turns out that if you bury explosives in the ground at a certain depth into the ground, at just the right depth, the propagation of the shock wave in the ground as it's excavating the crater simulates really well the same ejecta flow that you get from an impact, because by the time the projectile makes it, penetrates into the surface and creates that ejecta flow, if you bury an explosive at this right equivalent depth, you can get the same kind of flow. So you can make a very equivalent crater to understand, how the size of the scale, how the size of the crater scales with the energy of the explosion and the impact. And that's basically what we're doing here. So this is, dig a hole deep enough, put 5,000 pounds of ammonium nitrate fuel oil mixed in the hole. And then what I have to do is, you got to set that off. And the way you set it, I think I can say this, the way you set off the ammonium nitrate fuel oil mix is you have to use some C4. C4 is a plastic explosive. It's the kind that has enough of a shock that it will set off the ammonium nitrate. And so I'm sitting there taking the final cord, the yellow explosive cord that goes to the little switch that you push to make it all go. You put that in, and you massage a ball of C4 around that, and you put that in the middle of the anvil. And I'm sitting there massaging this roughly soccer ball size glob of C4, which is kind of like modeling clay when you're working with it. And I'm modeling it into the hole in this ball-shaped thing here. And as I'm doing it, it dawns on me that I'm supposed to be getting on a plane in Albuquerque in about 4 days. And no matter how well you wash your hands, when they do that little swab test with the little thing and they stick it, they're going to do. Fortunately, they didn't do the swab test on me that day, but I was thinking the whole way, I hope they don't do the swab test. I'm not getting on the plane. So there's the ball C4 down the bottom. They brought me 50 100-pound bags of Neanfo to dump in the hole. And that does something fun like that. So what I was interested in this case was not as much the size of the crater. I was more interested in distribution of the ejector with distance from the crater. How thick is that ejector blanket as a function of distance? And so you'll see in the video that I'm about to show here, you're going to see a little black dot in the middle of this field. That little black dot is that big round cylinder full of the ammonium nitrate. And then out, linear distances out from that is these little white patches, which are big sheets that I had kind of punched down on the ground to catch the ejector that I hit in there. So that's just a set of scale. So the little black dot that we're going to see in the middle of this movie, about the size of a bed of a pickup truck, just for scale. And this is 5,000 pounds of ammonium nitrate. Let's go. Oh, there it is. Oh, there you go. There's your 5,000 pounds of ammonium nitrate going up. What you're seeing, these all rocks that are falling back down, the ejector falling back down. As dust clears, if you will, you're going to see effectively a very beautiful scale model of the meteor crater, which instead of being I'll tell it 55 feet across in this case, meteor crater is 3/4 of a mile across. If you'd have been out there in the Arizona desert 50,000 years ago, you'd have seen a very large version of what you just saw there in that movie. Okay? And so it was really fun to walk out there. I've never walked on the rim around the edge of a large explosion crater like that before. I was not prepared to, I'll show you this from another direction here. From the side. Now we go from the side. You see the compression of the blast wave spreading out at the speed of sound. A little refraction through the atmosphere there. You see the blast wave, the intersection of that point along the surface of the ground here coming toward you, rising up dust. The reality is, meteor crater 50,000 years ago was sort of picking up sticks and picking up small stones and throwing them across the low ground at this kind of level, striking the mastodons and the ground sloths and the things like that were still walking around in northern Arizona at that time. The blast wave, if you're that close to be hit by the rocks, the blast wave itself ran into your body, would burst your lungs. You're going to die from drowning yourself in the blood in your burst lungs. Okay, this is why you don't get close to explosions. But these kind of high-speed videos allow us to understand and kind of, in our brains at least, try to scale up to understand what happens when a small asteroid strikes the surface of a world. Here's the crater that is formed from that. There's me down at the bottom here, walking around the side of the rim here. It's really neat. It's 12 feet deep, 55 feet across. When you walk down the rim, it's kind of fluffy. The ground has been bulked up by the impact itself. This same effect happens. The rim, if you've ever been out to meteor crater, you have to walk up the rim first before you can then move down into the crater. The rim of meteor crater today is not nearly as high as it was right after it formed. Part of that is because it's been eroded away. But part of it is that the bulking up of the crater rim has settled in over time as well. Most of it's because it's been eroded away. But the ground itself is actually kind of fluffy as you walk on it right around a fresh crater. Okay, the other way to do this is to just shoot projectiles yourself. Now, you could use that rifle bullet the way Gene did on TV shows all those years ago that I was fond of watching, but that's too slow. Even a rifle bullet is too slow for these kinds of impacts. Typical muzzle speed, a rifle bullet is on the order of a kilometer per second. Remember that the impact speeds out on the belt are about 5 kilometers per second. The impact speed of a small asteroid on the surface of the moon, or here on the Earth, by the time you're here in the inner solar system where things are going faster, those impact speeds are more like 20 kilometers per second. So we're talking very, very fast. But we can still at least explore the realm of physics with the main belt asteroids at places like the Ames Vertical Gas Gun at the NASA Ames Research Center in Mountain View, California, the Bay Area. At Southwest Research Institute, where I work, we have a couple couple of large guns where we shoot not just BBs, you know, little 16 to 18-inch size things at the Ames gun, and our guns at San Antonio, down the road there, to the east of here, our headquarters in Southwest, we have guns where I can shoot golf ball size things at those kinds of things. And of course, that allows us to get farther into the relevant scale of impacts of actual asteroids. That's very helpful. Here's the Ames gun. This was built in the, again, the run-up to Apollo, when people were wanting to better understand the crater formation on the moon and the actual impact process itself. And so this facility was put together to allow impacts at various angles. Each one of these little doors on the side of the big vacuum chamber here is an entrance port for the gun. There's a big screw here that will rise this gun up to various impact angles, all the way up to vertical, where it will shoot straight down into the chamber. It's a really neat facility. Inside the chamber itself, you can get in there. It's big enough to get inside. This is they were there filming a TV show when the production followed. We hang our meteorite rock targets inside the chamber. Here's one of the entrance ports where the projectile will come in from the gun, strike our target. In this particular case, I put aluminum plates, I guess they're aerogel on this. Sometimes I'll put aerogels in there to collect the fragments, analyze the chemistry. The foils are there to look at the hole sizes that are created by the ejector flying off, so you look at the size distribution. There's an example of one of the actual meteorites that we shoot, for instance, generated a picture like the one I just showed you. This guy here that you saw before. We have a lot of high-speed cameras. This is the neat thing. I'm going to show you a video in a second of what some of these impacts look like, because we've got these wonderful cameras, many of which didn't exist when I first started there. The very first time I ever went to the East in 1995, they were still using the old film cameras, high-speed film cameras, where they get ready for the run, and you would hear the camera spin up, you know, like a turbine that hits this girl, spinning up, shredding the first several hundred feet of film that ran through it. And then right at the point of impact itself, you're catching, you know, maybe 1,000 frames per second on the film or something like that. And then you send the film away for 2 days, it comes back, and you look at the results. Nowadays, we've got these wonderful cameras, digital, very light sensitive. You run the impact, and you know what? As fast as JP can type on the computer the key, the file brought up, within 30 seconds of the impact, you're watching the impact in slow motion. These cameras are running. We typically will run them at speeds of a few 6,000 to 7,000 frames per second. These cameras up there, I can run at up to 1 million frames per second. Okay, that's fast enough to actually watch the projectile come in, merge into the target, and watch the cracks begin to fragment, you know, propagate through the target itself. So you can learn a lot in that. And so it is again what we've got. Let's see if I can. You're going to see this is a 1/4-inch aluminum bead flying in from the side here at 45 degrees, straight in the middle of the pan, creating an actual impact crater. There you go. You're going to see this again. And I'm going to talk you through the physics of what's happening as the crater forms. Okay, there's the crater forming. Look at this surface right there, this concave boundary here as the ejectile sand grains are flying up. Watch it transition from being concave to convex. There's kind of straight, and now it's turning into a bit of a convex. That boundary, concave to convex, that means the crater is not forming now. The crater itself is formed, settling in a little bit, but the ejecta is now continuing to fly out there. Every individual particle is flying on a ballistic trajectory. But the ensemble effect of the particles being ejected from the same place at the same time gives you this effect of this wall, this curtain of debris that propagates out from the crater. Here is one of these million frames per second impacts, the cracks propagating through the granite block. This shows you the energies involved at 5 kilometers a second. You melt rock. Okay, that glow, that molten rock from the energy you impact. All that kinetic energy has a ghost, and it goes to the melted rock. Here's a piece of basalt being fragmented at that speed. And again, you see that power law distribution of fragment. This is what's going on out there in the main asteroid belt. Every time an asteroid runs into another asteroid. This is what happens when the fragments of impacts that resting on the surface of the moon or another asteroid, when those blocks get hit by micrometeorites or small meteorites. They get further fragmented. This is why the surfaces of the moon and the asteroids are covered in what we call regolith, this rocky soil of broken up and darkened fragments and bits. This is where the fine, dusty, powdery surfaces of the moon and the asteroids originate from. Now again, this is all at this sort of size scale. But I'm one, if anything is worth doing, it's worth overdoing. And so it's worth going to larger scales if you can. And so I go to our guns in San Antonio and shoot even bigger targets. And we're seeing tail and some of these other impacts that are going on. But I'm leading you up to, you're going to see a big round granite sphere, which is literally about this big. It's a meter in diameter. And this is one of those impacts where I'm shooting the golf ball size projectile. And at the very beginning of that video, you'll see the golf ball projectile flying in like 1 or 2 frames. You'll just see it flash before you enter the rock. Yeah, this is one of these higher frame rate things where you just, it's rocky destruction ballet, you know, it's just, it's a fascinating thing to watch this process of online. Yeah, there you go, this is our you'll just see the aluminum projectile flashing from the left. This was an impact test I was doing to test what's called kinetic deflection. This is what the DART mission that's heading off to a small near asteroid right now as we speak. I'm a science team member on the DART mission, and so we're doing impact experiments like this to start to give us larger scale, more lever arm to extrapolate our results to relevant size scales of what's going to happen when the DART impactor strikes the moon of Little Didymos and makes it change the orbital speed of that little asteroid. So we can basically test the idea of pushing a threatening asteroid out of the way someday by impacting it with a high projectile. It's called kinetic deflection. Okay, very quickly, I'm running along here, and I'm not going to get into using all the fun vehicles here. So, early on, I said that impacts are the dominant geologic process for most asteroids. For the nearest asteroid, maybe not so much, it turns out. As we now know, it turns out that the action of sunlight on small objects can actually push their orbits around a little bit and spin them up over time and change their rotation rates. These are a couple of various effects, the Pointy-Robertson effect. The thing that changes the spin rate is something called the York effect. I want you to type the acronym. Look it up. It's a really neat effect where the infrared, the heating effect of sunlight on the rocky surface of this world, as that heat is re-emitted in the infrared on the afternoon side of the asteroid, it acts like a little push on the asteroid itself. It can either affect the orbit of the asteroid, the Yarkovsky effect, or it can affect the spin of the asteroid, the York effect. And it turns out that little rocky worlds that are already just piles of rubble can be spun up to the point where it changes their shape and actually causes them to fission and spin off moons. That's the other process that can actually create moons of little near asteroids. And I'm going to show you a movie about this. How do you make a Bennu or a Prude, these 2 asteroids that we've now visited in person with the OSIRIS-REx mission and the Japanese Hayabusa 2 mission? I'll show you pictures of Bennu in a second. It's a really neat asteroid. Both of them are these spinning top-shaped asteroids where they're spinning so fast that they bulge out at the equator. All the loose material on them has spread out to the equator, almost at the limit of just flinging stuff off at the equator. You could go there to the equator of Bennu or Ryugu, you barely look at the rocks there and they float off to space because they're just barely hanging on a vertical limit. Okay? Here's how you make them. Like, the first thing you need to do is you need to make a robot. You need to have an original target body that is itself mostly just a big pile of stuff and cobbles and broken up fragments that can be dumped out of a dump truck out in space and have its very feeble neutral gravity barely hold it together. So the first thing you do is you break up the asteroid. And you've seen this movie before. Then you have to reaccumulate the fragments, and you do that by, again, this very feeble self-gravity. And enough to show you a numerical simulation of a couple of balls of rubble that whack into each other, and very accurate numerical calculations of self-gravity reaccumulating those fragments. And then you let sunshine shine on it, and you're going to see a picture of this rubble pile from the side, from the top and from the side. And you see, as it spins faster and faster and faster, it generates this shape where all the loose stuff, the orange stuff, is flung out around the equator. And in some cases, some of that loose stuff that's flung off will reaccumulate and enter orbit around the asteroid and create a small satellite, which you see here from the top and from the side. And so the result is this top-shaped asteroid, which we may or may not have known, but top-shaped, that's the key. Here's a picture now of Bennu, half-kilometer diameter, near-Earth asteroid, C-class, very, very dark, but albedo is about 4%. Go to a laser mirror and pull out the black toner cartridge material that is feeding the laser mirror. If you ever had to do this in the office and you get this stuff on your hand and you go, oh crap, and it just comes with black, okay? That black is not even quite as black as Bennu is. That's how dark 4% of you is. The only reason it looks bright is, of course, that spacecraft exposes to actually see something. But if you were walking around, it would be black. But this top shape is due to the spin-up, the rapid spin-up of this ball. This is Ryugu, the other, this is a kilometer across, twice as big as Bennu, but it's got that same top shape to it. And you see all the rubble, all the rocks, and the debris on the surface. This is years and decades and millennia of small impacts breaking up and breaking up again and breaking up all the rubble on the surface of the asteroid. And you can see the scale bars here. So you're looking at, you're looking at rocks and things like that that would fit in this room. And I guess maybe in some of the bigger cases would be about the size of this room. I used to have a picture where I put a sports car there for scale, and you can see the scale I can show you that. But this is what's going on. And we can simulate these, I'm running long through this. We can play games, and the games done to make features much like what we see on these objects. And the beauty is we actually go on there and sample. This is a still image, a self-portrait of the Hayabusa 2 spacecraft taking a picture of its own shadow on the surface of Ryugu just after it has touched down and grabbed a sample off the surface of the asteroid right there. What you're seeing is the dust and debris still floating out around from the impact point in that very, very feeble gravity. What does that look like in motion? It looks like this. This is the collector arm, the sampling arm on the OSIRIS-REx spacecraft, doing the same kind of touchdown sampling on the surface of Bennu. I'm going to put this in motion for you so you can see how it looks. No, it's not bad. Not bad. There we go. Okay. Coming in, coming in, coming in. And then, very quickly, get out of Dodge before you get to the spacecraft. But that allows us to collect several grams of this material, which is not going to be back to Earth for analysis. I forgot to provide next year to grab that already. So, we're going to be bringing back samples of this asteroid. Also on its way back now are samples of Ryugu from Hayabusa 2. And here's what I find fascinating. There are numerical statistical models of where both of these asteroids came from that suggest that they could actually have originated from the same parent body of. And so it'll be really neat and disappointing at the same time. If we get these samples back from these two completely different asteroids, and it turns out they're exactly the same thing. It'd be really neat on the one hand, because it would verify this one numerical statistical model. But it'd also be a little disappointing, too, that we've gone and spent all this money to sample the same thing for us. But either way, it'd be really neat, but pretty neat. So what this highlights, though, for me as a cave diver, the fascinating properties of the surfaces of these little rocky worlds. Okay, imagine doing a ISS or repairing the Hubble Space Telescope spacewalk in your spacesuit with all your tools tethered to you in microgravity, all that high finesse work that you have to do, because that's what the surface gravities are like on these little worlds. They're so small, it's effectively like being in zero G. Except you're on the very dirty, dusty, flyable surface, much like doing an Apollo moon. Okay, this is something we have no experience with operationally in astronauts. And that, I think, is going to be our next giant leap. As we're getting ready to go up to Mars, and as we're developing that capability to go to Mars, we're also developing the capability to go and experience worlds in person. And that's important because, one, they're an impact hazard. We need to know the enemy, so to speak. We need to be ready to understand their surfaces and their interiors at a much higher level of fidelity in case we ever get pushed out of the way one day. They are literally gold mines in the sky. They contain, a lot of resources that we're going to use to have a thriving, running economy in space. We're not going to be hauling materials from the Earth out of the deep gravity level we're in. We're going to use the resources that are already out there, effectively for free, because you look at them as they float off the surface. Okay? We don't need to be hauling stuff out of gravity well here. So we need to understand these worlds, and I think it's going to be an incredibly challenging and fascinating operational environment. So I'm going to end there because I've gone long, and if you have any questions, I would love to.
Your shirts over here. What would you say is the mass of the main?
The question is, what's the total mass of the main asteroid belt? So most of the mass in the main asteroid belt is in the largest asteroid series. And if you could pile up all the material in the asteroid belt and put it into one world and make a little round bump out of it, it'd be maybe on the order of a third the size of the moon. So there's not a lot out there. Here's the other way to understand how little stuff is actually out there. Right here. Scale model of the solar system. 12-inch globe that we know from our classrooms. Very common here. Many of us have been sitting in our office dead. Okay, we all know 12-inch globe. Let that be the sun. The Earth's scale is a BB, 107 feet away from that globe. Okay, maybe over there in the corner of the room there, and here's this BB. Okay? All that material in the asteroid belt, the size of a grain of sand, 300 feet away. Crush it up, scatter the debris from that one grain of sand in a circle 300 feet in radius around that group, around that thing. All of that is in the asteroid belt. There's not much there.
What happens if it like misses?
I'm sorry, what happens if?
So what happens if they all impact like misses?
Oh, the impact, it occasionally happens. We have a laser on the gun that shines down barrel gun that's bore-sighted and put a projectile with. That produces a little spot on my target where I can place my target. It's pretty good. The accuracy is about the size of your fingernail, so pretty much anywhere inside your fingernail is where that BB's going to hit. Sometimes, though, when I'm shooting the very smallest targets with the very smallest projectiles, I've had it miss a couple times. And that wastes about $6,000 worth of gunpowder and gas and stuff like that. So it's not a fun miss.
Is the asteroid belt essentially all in the same plane?
Is the asteroid belt essentially in the same plane? Yeah, the inclinations that you'll see amongst some of the asteroids are higher than the typical inclinations that you'll see in the major planets. That's not too surprising because they're small objects that are easily perturbed by the gravity of the big planets, and so they've been pumped up in eccentricity and inclination over time. But effectively, yeah, think of it more like a torus than a disk. But yeah. Do you want to bet who gets asked on any better or right?
Right there in front.
My question is on formation. How do ionized atoms become molecules, become dust, become chondrules, become asteroids?
Right.
How does that happen if they're traveling kilometers per second.
If they're traveling, yeah. So I'll just repeat, just in case you didn't hear, it's a whole formation issue. How do you make asteroids out there, and how do you make anything out there in the early protoplanetary disk when you need to accumulate, molecules and dust grains into rocky worlds when these things are running into each other at 5 kilometers a second? How do you do that? The answer is that originally they weren't running into each other at 5 kilometers a second. That 5 kilometers a second speed that we see today with the impact is a remnant of the fact that the main belt, all those orbits have been pumped up in inclination and eccentricity by the gravity and the perturbations due to Jupiter and Saturn. Back 4.6 billion years ago, when it was all accreting to start with, the remnant dust grains from the interstellar medium that were in the cloud that became our solar nebula, those grains were supported by the gas pressure in the protoplanetary nebula, and they were moving around the sun in much more leisurely pressure-supported orbits. And there were electrostatic effects, there were sticky organics that allowed those slowly drifting little bits of grains to stick together and actually grow into dust bunnies and grow into larger objects. Now, the conundrum is that as you grow these cotton candy dust bunny accumulations together over time, at a point they reach a certain size scale where they're so fragile that even at those low speeds, they tend to, instead of sticking together to make it get bigger, they tend to start ripping each other apart. And how do you cross that boundary? The answer seems to be gravity, probably. And the disk generates enough of that material that self-accumulates, it self-gravitationally accumulates into planetesimals right, you grow them by fiat, so to speak. But the initial stages really is kind of a, dust bunny accumulation under your bed process. We've done this on the space station, I've done it in zero-G aircraft. There's a lot of uncertainties, a lot of unknowns yet in that process, but the basic idea is dust bunny accumulation. That's the initial stages.
Let's get up this side of the road and keep on, we've got to move on to the moving program. Right there.
Right, yeah. The question is if you're an astronaut and you're actually going to one of these small worlds and you're going to start interacting with the surface, is that going to affect its orbit in a way that might create a problem for us? Potentially, if you pick exactly the wrong target. But the reality is that just about anything that we can do to push on these objects is going to create such a tiny anything that a human explorer is going to do there. This is not ramming into it at many kilometers per second. This is going and interacting with it like this. Those kinds of changes in speeds are probably not going to have any real effect. The other thing to do to make sure of that is we're going to pick targets to go and play with that really can't be pushed into anything dangerous. So that's the strategy. You want to do like maybe one more and then?
Right here, the hand in the very back one up first. You.
Just a quick question. It was beautiful some of the impact modeling that I saw, but also quite theoretical in the sense that I could see sort of rays coming out, say like if I look at Tycho, I mean, when you see sort of the ejected coming out of many of these types of collisions, you tend to have sort of clustering.
Oh yeah.
And if we look even closer to home, we look at the Chesapeake Bay crater who's underwater. It's a relatively small crater, and there's really only on land rays of ejected coming. And when I see here, it's sort of entire splash of beautiful sort of hypothesis. And I'm wondering how you can rationalize and make that a more practical prediction.
Yeah. So in summary, basically, if you didn't hear it, as long as experiments and the model things all look very beautiful and symmetric. The reality is, when you look at real impact craters, you see rays ejected. It's very sloppy and it's very messy. And the answer to that is, it depends on the type of experiment, the type of phenomenon you're trying to study. When I showed you that impact splash in the sand in the first part of that video, that was purposely made to be a very idealized, beautiful crater so you could see all of the features of the ejector curtain and so on. Later on in that movie, though, you saw very irregular shaped blocks being impacted, much more like what a real impact is. Nature is messy, nature is sloppy, and yes, the reality is you tend to have rays of debris, and you don't get perfect spheres in nature. You get oblong rocks that only half crack apart, and most of the rest of the ejector goes that way. So the challenge is the balance between. Typically, what we'll do is some of these experiments are done in an idealized form, so that we can then match it to an idealized numerical experiment, which is what's teaching us about the way the fragments happen in any other generalized case. That's kind of a chain of argument. So very often we'll use an idealized, geometrically uniform target, so you can match it to what we are capable, or at least were capable of doing in the computers, so we could then match to nature. Nowadays, we're able to do some of these computer simulations with all those weird asymmetries, and we don't need to worry so much about doing our impacts with perfect spheres. We can just do statistical studies of break up the rocks, do 10 experiments on the regular shape stuff, and take the average of that, and that works well for numerical models. So that's kind of where that is. And I guess with that, we'll move on. Right, corner me after, and we'll talk in the hallway. I'm happy to chat.
Oh, yes, I was going to say, Texas giveaway, have at it, it's all yours, free for all. Don't let it escape without answering your question. In my introduction, I mentioned that he's a pilot and a diver. He's very much a Renaissance man. I forgot to mention that Don is also Dan is also a very accomplished space artist. His artwork is exquisite. So, and let's start with let's give you a certificate of merit to add in your collection.
Oh, wow, thank you. Sure, my secret. I said thank you.
The Big Texas giveaway is next, but I know the Earth sucks, and you've been stuck in that chair for about an hour now. I'm going to give you 2 minutes to get up and stretch. And when you begin the Great Texas giveaway, I want all the kids in the room up here. We've got a separate special thing to watch the giveaway specifically for kids. So I'll see you in 2 minutes.
Good job.
We're going to have to do something with a lower light camera.
Okay, call road prices, you'll fill up here, if you have a tank, give it to Emilia. Yeah. Just so everyone knows, dark out doesn't start until
Well, I came up with the design, and then someone.
Amelia's asking for the glorified colors to be poured up in the case. Glorified colors, you know what
It's crazy. We were on camera.
I'm sitting home by now. You know, that's, I saw one, I don't remember if it was in the Cosmos, it was a different document, but it shows it like, almost like skipping up, and then it wasn't like a direct impact, you know? Yeah. Right, right.
I mean, I got there at the gift shop. So how you get that?
So we created a everyone gets out so we can get started. Just as a reminder that everyone's attention. Could I have everyone's attention? Just as a reminder, dark out will start 1.5 hours after the end of the Great Texas Giveaway. So once we're done, consider what you do for the next 30 minutes. On that note, we have all, everyone has turned in their ticket, right? These are not halves of tickets. You just drop your ticket in there, that's a name, we'll call it.
Last call, everybody who's not put their ticket in the box. Okay, go on the bill. You only have two.
I'm not a kid.
How old are you? You're 2. Seriously, we have 15 years registered as a start point. Percentage to the high gas prices, 20 years, etc. But are there any more kids here today under the age of 18? You know what, buddy? You're the luckiest guy here. Here's the deal. We're supposed to have a bunch of things. We got all these prizes. We got one kid. So, you made a good choice. You have a little story. You do? Well, this is a Celestial Explorer, the Explorer, starts out. This is a Star Adventure program, which is everything you need to do to get some water out of the garden. We use that camera and tripod. You get your thing.
One thing else, because I already have a good telescope.
Well, sorry for the yes. Do you have a camera or do you have a camera? You want it? That means that you're in Sweden. That means I was playing for kids. You get plans here, red plans and let's get this thing going. We got, my goal for the next start party is to get 100 more plans. I kind of overshot. We got about 140 of them. So what I'm going to do is speed things up instead of giving them out all the time. If there's a group of the same thing, I will draw X number of tickets, even all of that one thing out. This is going to be particularly useful for this already let's class as there is like COVID areas. So, in no particular order, we'll start off with the contribution of Bob's Knobs, a 17.3 Delos eyepiece. Starting off with one of the big ones. That was it. And Michael Fred. Michael Fred. Yours. From the media people up at the Vintage area, we're just talking about asteroids, planetary impacts. This is a piece of Vesta, the asteroid Vesta, certified, guaranteed to be a piece of another world. And this is going to Alan Myers. And another piece of another world, the wife of the asteroid Angie Goldman, she's got this necklace made out of material from a comet impact. So this is going to go to, hopefully, the young lady. Greg Roman, it's going to look lovely around. Greg? Greg Roman? Y'all know the rules. Must be present to win. Greg Roman, is that you? Hey! And the next one is something very useful. Keep the light pace on you, rescue your computer. Compliments of case rates. And this goes to Roy. Next up, we'll do 3 tickets from Firefly Books, the Hubble Space Telescope, the Firefly Planet and an autograph copy of the Back Astronomer's Guide. And be sure to look at all the pictures and just look at them online. And this will go to Steve Coleman, over here. Steve Coleman. And let's move to, oh, wait a minute, these are 3 separate things. Whoa! No, 3 separate things. Oh, mistake. Only the book was yours. And the whole book goes to Ernest Evans. Ernest, over here. Another people. 3 tickets. Compliments of 365 days of the moon. Very known as Week. 13 by 19 prints of Tycho crater, Plato crater, and Copernicus. And the first decoration for your office wall goes to Kelly Moore. Don Morris. Don Morris. Don Morris. I see fingers pointing, he's here. Oh, yeah? Okay. One of you. Gene Fioretta. Gene Fioretta. There we go. Okay, getting some practical things. Lithium LP power tank. Everybody has a telescope. It's electrically powered. Needs one of these. So 3 times. First one goes to Brian Weissman.
Look at that.
The second one, Stephanie Anderson. We're going to power you up. I know you're here. Okay, that's I'm going to give you the right people move on here. Next ticket will get $50 of TSD cash. That's not the acting on that. You know what you're buying. And Matt Holder, City of lovely clay trees, and if you ever see them up close, they're very embossed with astronomical symbols. And she painted some silk and art, and we just donated the Princess Caroline, and the person who enjoyed that will be William Beckett. And more homegrown prizes. The Davis Mountain Rock Shop in Fort Davis put this up just for us.
Oh, wow. That is cool.
And she told me what all rocks were, what the stones were, and geologic meaning of them. But I'm going to smile, I'm not a geologist. Just say it impressed me, and I hope it will impress. See you later.
Oh, nice. That is awesome.
One reminder of this, Gary Solano, compliments of Sky Telescope magazine, goes to San Miller. The next one is a national photographer. Compliments of Bruce Burrell, national photographer, said that he is my 5'2" guide planetary camera. I use these myself. Cool things. And is Martha Bowers, a national photographer. Martha Bowers. She is. And free tickets, compliments of our friends at Celestial, vibrations trusting pads, free bye-bye, 3 times. First one is number 2, Christine Alligator. Second one, Jerry Hughes, Don Travis. And the third one. First one is going to Tim Parsons. Calvin Carter very generously gave us 10 red headlamps. Everybody needs these when they're set up in the dark. We've got 10 of them, and then we can all sort of have it as a box. So the first one, 2, yeah, we did this, Cody Reagan. John Paul Watson. Larry Mitchell, you can write it down. Dan Durda. Dan Durda. We have a good question because he didn't have a chance. Okay. No Davis. No Davis. No Davis. Must be Stephen Barrett. Mark Mirage. And Gene Paul, come on back. I did call you this time. And one more for the batteries included. Goes to Kelly Walker, no, Chrissy Walker. Chrissy Walker. This is very interesting. So, Debbie, and it's Debbie's light pollution demo kit. But it's also a damn cool desktop. So if you're not into demonstrating light pollution, it's very useful. But if you are, it's quite useful in city council meetings, doing light pollution demonstrations. Items for that, there's like slide elbows, set of brightnesses, and $200 action figures to demonstrate the light pollution things. So this could build Prude Ranch, TRINBOI, Prude Ranch, back there. And hopefully a lot of you are subscribers to the Amateur Astronomy magazine and enjoy my publications here. But if you're not, you're going to have a chance to catch up on the past 10 back issues, documents of Amateur Astronomy magazine, which are 3 times. So if you're like that I'm reading, Paul McCallum. And Chris Over. Chris Over? Eli Wood. And David Heffenauer. There he is. Paul is not here. So we have another shot of this. And Justin Victor. back in. Are you ready for this? 20 of them. Compliments of Steve Ramsey, who better known as the operates his outreach program in Southern Airport and Charlie Gates Solar's planning project. And he donated 200 solar classes. And so I'm packing some other packages with 5 each family packages to get 40 people here at the USD ready for the great solar eclipse crossing right in our own backyard. So, Mike Ross, Mike Bruce. Fernando Torres. Richard Papier. Douglas Dawn. I guess my voice is just not, this is Dawn. Douglas Dawn. Yeah, my voice is fading away. I'm sorry, people misunderstanding me. Manuel Vasquez. David Williams. David Jim Gillis. Rodney Rocha. I'm going to assume there's something skipped here. It's actually the moon. So, uh-oh, there it is. They wrote the name on the wrong side. Scared me for a minute. Jeffrey Wall. Very yes. Jim Paul. French. That's it. And in this insert, let's one more big step. And
Francisco Blue Water Ride. Ah, yeah, there it is right there. What do you want?
Robert yeah. Wayne Horton. Then Philpott. I guess I'm full. Okay, since we do classes, we'll say class number. That's not good. What's that? Anyway, Greg Hubbard. Manifold, 7 years. Leslie Reed. Rivera City, you're ready for this. And lastly, Chris Leslie. Chris. Next up, $50 for CSP cash. Compliments of the sports scientific, more red flashlights, so will be illegal at night. So 4 times the red flashlights. Compliments of the sports scientific. Edward Hughes.
Congratulations.
Christy O'Reilly. Christy O'Reilly. Paul Prison. To make sure everybody with a red light flag is flags green. Flags green. And then Gillard. Ed Gillard. Ed Gillard. Is it going to make it outside? Okay. Going once, going twice. Must be present.
Oh.
Nathan Mayer, present. For Robert Snyder. Robert Snyder. Robert Snyder.
Bob.
Another restaurant, our telescope, and our technology. And more power to John Morgan. Okay, so far this Tuesday, we have immediate news of how this is restaurant, to the Lowlands hand warmer. And Alfred Maurer will be warming his hands. Alfred Maurer, there he is. As Larry Rafferty. And the last name goes to Simon Tang. Simon Tang. And compliments and scores scientific, we have a Julian Plant series, which I hope you can long as it's because he's a senator 40 something degrees Fahrenheit. Anyway, you know what to do. And Brandon Liddell will be plants here. As was Bill Peters. Bill Peters. I knew this one. Bob Logan, Rock Larry. And one final here to Bill Nation. Now we get into this, the gifts and tickets. Like I said, there is a lot of goodness this year. My neighbor Pitch is sitting here. But there's a pure you know what that is. So we started on with Bob Smiles. Combination from screws or whatever telescope you've got. SCP, usually whatever. Good plans for Bob Smiles. First one, Ted Sager. Ted, comment yourself. Ted Sager.
He's here, he's outside.
There it is. And Calvin Carter is now. Two tickets, compliments of a free period to spectral posting. These things are cool. They show all the elements as their spectrum. And they're really unique. I think you'll enjoy them. The first one to get spectrified is Mike Honig. Mike Honig, and the second one to get spectrified is another guy, Mike Valentine. Mike Valentine. And raise the national set here in Texas 4 times a $50 gift certificate for anything to order anything on the AstroZet website. And the first one is Alfred Miller. Alfred Miller. For the orchestra. And who else is going to do an Astros? Catherine Gelson. Catherine. And the final person is Robin Morgan. Robin Morgan. The next four, compliments of Pizza Insight. Yes, we're done. So I hope this this is a gift certificate for one live or one recorded Pizza Insight workshop. This $35 something simple. Bob Van Vliet. Bob Van Vliet. And the next one to insight is Orion. Orion. And Thomas Lowe. Thomas Lowe. There it is. And Greg Jones. No, John Jones. And he did this. Also from this insight, one individual good for a 1-year subscription to IP Fix Insight tutorials. Catherine McCall, I hope you are able to ask to start it or no. Catherine McCall. Catherine once. Catherine twice. Catherine Dawn. Catherine Gordon. Subscription, Lawrence Simpson. Lawrence Simpson. Ken Concepts couldn't be here this year, but they said, I'm going to let this year for anything on the store. It's a big part, that's a big part. And that goes to Eddie Pavino. And my friend Phyllis and I, because the night we're going to that plan, good software, I did a review of it one time. And that goes to Jerry Barker, who can plan his observations now. Jerry Barker. From Boston, this is the BBC News, a pinpoint astrometric license. I was going to say something, but it's still in my head. Anyway, Stephen Grimsley can get pinpoint. This plate solving for the astrometric. And all done, and also pretty. And my friends at Lansing Sky in Houston, actually America, they made a $200 gift certificate, good for anything in their store. Goes to, thank you very much. Thank you very much. I'm so sorry. For the Building Systems, a 1-year subscription or extension to Photoshop Lightroom, which goes to Alan Top. Alan Top. Hope you got Photoshop. I'm very welcome to one more year. And our friends at Software Biz, the Sky Imaging Edition goes to Angie Coleman. Angie Coleman, there she is. Principal Scientific, a visual zooming test, zoomer test. Which I hope Laura had you as a camper. Not sure which one got the grand prize. Well, we got the DX 130, and we've got the Fred Richard. Let's go on this. Who wants? We got two excellent things. We got the Star Citizen Story, yes, whatever it is, and we have the Star Richard Pro Pack, which is everything except the camera and tripod. Who wants this to be the grand prize? Or who wants that to be the grand prize? Sorry, that's the beginning. We're voting on this one will be the grand prize. Star Richard? Or it's lessons in school. Okay. Next, since the DX 130 is in telescope, you're going to no, actually, I just discovered a pile of stuff up here. Anyway, this is yeah, that's quite a few things up here. We got moved on, and I didn't realize it. Okay, now we got prejudice, please. The other one from Hubble Optics, artificial star formation tool. And Thomas Lewis, and I'll make it in the dark. Yes, without stars.
Brandon.
And Susan. And lastly, Nathan Morgan, and colonnade without stars. Nathan Morgan. From these rates are Timmy, Rick Batchelor, Scott Mitchell, right your way. Friends, welcome. Ladies and parents, three of you. Very important bulletins here. We have Dusty Hawkins and Michael Neighbor, who does his office. And Joe Palau. And lastly, he does the office, Joe Sutter. Joe Sutter. From our friendly Gene Astro, a 26mm DSO. I'm not sure if this is a one or two, but once in this to figure out which one it is. Where? Now we really have learned the final one. These starting to go. I've had one of these things that we resolve one. So this is it. Go there. Do it. Scott said an announcement he wants to make for your show. Happy ones. Grand prize. Kurt Meyer. Very good. So the rest of this is going to have to get talk. It's been fun. I'll turn it over to Scott Mitchell now.
Well, thank you. Do I get him a card or something? Or no, they didn't have this card.
Just go home with it.
Cool. You know who the vendor was? Who I
Skywatcher.
Skywatcher. Thank you very much. So I did. Thank you.
You said you won't be judgmental. And even if your telescope is a patchwork, Chevy ever something happened live, it will try to find truth and beauty in your work. Absolutely. Yes.
Ladies and gentlemen, it's 30 minutes to dark out. Please, if you need to use your lights to drive. Do not drive without lights. 30 minutes to dark out.
This is Deborah Bird.
So Will has the links to the live stream of that. Could you write them, type them, text them to her tonight? No. Here's the thing. She's also with FirstSky.org, and they're going to publish it tomorrow morning letter, but they need their deadline to 7 a.m. tomorrow. And so she needs to certify So it's only on Facebook. Okay. If you text it to her number, okay, thanks. That's all. Yeah. I'll let you two work it out. Yeah, that's crazy. It's kind of buckled up. Yeah. Always. It's not worth